Okay, so again, in Anna's coordinate system, she just sees the light pulse go up and down. It's detected at the same place that it was emitted from, and so she sees no difference. So these two events, the emission of the light pulse and the detection of the light pulse, take place at the same point in space. And so delta x prime is equal to delta y prime is equal to delta z prime is equal to 0. On the other hand, she sees that she does see a time difference between these two events, of course, and it's equal to the total distance traveled by the light pulse divided by the speed of the light pulse, which is just the speed of light. Okay, so obviously c delta t prime is equal to 2L. Now, so what that means is that for Anna, the interval is just 2 times L squared. Okay? Now let's see what happens for Bob. Let's see what Bob observes, rather. Okay, so what does Bob see? He sees that, in fact, the light is traveling, the events of the emission of light, the reflection of light, and then the detection of light, these all happen at actually different places because the card is moving to the right while he's observing in the earth frame, in the rest frame of the ground. Okay, so he sees the light path go like this, and because this is sort of a clock, that is that for Anna, the emission and detection of events happen at the same time. So that time interval is a proper time. It's like a clock. It's an interval between two different events that happen at the same place. And so basically Bob sees that time interval dilated. Okay, so for Bob, he sees that c times the time interval between the emission and detection events is equal to gamma, right? Basically this expression up here, gamma times c delta t prime, which is equal to gamma times c delta t prime is just equal to 2L. Okay, now he doesn't see length contraction because there's no object. If we ask the question, how does he see the cart, the rail car? He definitely sees the rail car contracted in the x direction, but we're not asking that question. We're just looking at three different events, or two events, the emission and detection event. And so he doesn't see length contraction, but what he does see is that the cart has moved a certain distance between the emission and detection events, and so those two take place at different points in space. Okay, and so delta x, what he sees, is just v times delta t, which is equal to beta c delta t, which, as we just wrote down, is equal to beta times gamma times c delta t prime, which is equal to beta times gamma times 2L. Okay, so let's now work out on the next slide, since we've run out of room, what the interval. We've already just calculated the interval for what Anna sees. What's the interval for what Bob sees? Okay, so the interval for Bob is just c delta t squared minus delta r squared. Now, since delta y equals delta z equals 0, then delta r squared is just delta x squared. Okay, so if we write down what we had on the previous page, so c delta t squared, as we saw, is just gamma times 2L squared, and delta x, that is, was equal to beta gamma times 2L squared. Okay, so that's the interval she sees it. If we work out the math and if we factor out a 2L squared, okay, and we factor out a gamma squared, which is in both as well, then we're left with 1 minus beta squared. Now, if you look at the definition of gamma on the previous view graph, gamma squared is 1 over 1 minus beta squared. And so this